Greetings everybody. This video will hopefully explain the last topic that we'll cover in chapter 6 and that'll head us into exam 2. This deals with Newton's Universal Law of Gravitation. Well, it states the following. We'll worry about the whole geosynchronous satellite in just a second. But it simply states the following. Consider any two objects in our universe. Call them M1 and M2. Well, there's this gravitational attractive force, meaning this pulling force. There's a gravitational attractive force between M1 and M2, given by F is equal to G M1 M2 over R squared. Well, large G is the gravitational constant. In MKS units, it is 6.67 times 10 to the minus 11. And its units are Newton meter squared per kilogram squared. So that's G. M1 and M2 are obviously the masses of M1 and M2 in kilograms. And R is simply the distance between the centers of M1 and M2 in meters. Remember, think MKS always. Well, it applies to any two objects in the universe. You know, you could have a pen and a pencil sitting on your desk. The pen is M1, the pencil is M2. R is the distance between their centers. Well, there's this gravitational attractive force between them. But then you might say, well, how come they're not moving? Well, remember, it applies to any two objects. So there's a force between the pen and the pencil and your lamp, the pencil and the pillow on your couch, etc. So the real practical application is is when it's applied to planetary and satellite motion. So really, Newton's universal law of gravitation, F equals G M1 M2 over R squared. Well, for practical things, it's planetary and satellite motion. And some examples are, the moon orbiting the Earth orbiting the sun, and 3, geosynchronous satellites orbiting the Earth. And that's the example we're going to focus on. It's really one of the most practical applications of Newton's universal law of gravitation. And of course, it's an inverse square law. Well, geosynchronous, what does that mean? That means that the period of the satellite's orbit, typically when we talk about UCM and we talk about the period of the orbit, no matter what it is, we use an uppercase T. And the period, by definition, it's the time it takes the object to do one complete circle, one complete orbit. That's large T. That's the time it takes to complete one orbit, i.e. one complete circle. That's the period. In MKS units, it's in seconds. But typically we use an uppercase T to indicate period. Again, what is it? It's by definition the time it takes to undergo one complete circle. UCM, uniform circular motion. Well, all geosynchronous satellites, remember, their period is the same as the period of the Earth's rotation about its own axis. And remember, the Earth rotates about its axis once per day. So all geosynchronous satellites have an orbital period of 1 day, which is 24 hours, which is 8.64 times 10 to the 4th seconds. And we'll find out, we'll prove that all geosynchronous satellites also orbit the Earth at the same height. And so here's a sketch of a geosynchronous satellite orbiting the Earth. So M1 would be the satellite, M2 will be the Earth. The satellite orbits at a height h above the surface of the Earth. Now, there's the force represented by the universal law of gravitation. It's the force of the Earth pulling on the satellite. And here you can see the satellites, in this case, the satellite's moving counterclockwise, indicated by this arrow right here. That's not a force, that's not a vector. That's simply telling you, hey, the satellite is moving counterclockwise. But it doesn't matter. There's your F, given by, in general, G M1 M2 over R squared, where M1 would be the satellite, M2 would be the Earth, R is indicated by the red here. That's the distance between the centers of the two objects. Notice here RE, large RE, that's the radius of the Earth. You see that? That's what that means, RE, meaning radius of the Earth. And notice H. H is the height of the satellite, the geosynchronous satellite, above the surface of the Earth. So clearly, for the satellite, its radius, R, is RE plus H. Nothing complicated, just look at the figure. But that's a sketch of a geosynchronous satellite. And it's undergoing UCM. It's orbiting or circling the Earth. It's orbiting at a constant speed v. And it's remaining at a fixed height, h, above the surface of the Earth. Well, clearly the radius indicated the dotted line circle. That's the circle, that's the UCM of the satellite. Clearly that radius, little r, is RE plus h, the radius of the satellite's UCM. Okay, well remember, no matter where the satellite is on this circle, F, given by G m1 m2 over r squared, F will always be directed towards the center of the circle, i.e. it's always going to be positive in terms of UCM. Okay, well let's go ahead and let's apply it. So here, the centripetal force acting on the satellite, as indicated right here in the figure, the green, F is G. Let me step back. So we know that that force is going to be given by the Universal Law of Gravitation, where the objects are me for the mass of the Earth, ms for the mass of the satellite. So Newton's second law for UCM for the satellite, we have the sum of the centripetal forces is equal to, remember, the satellite's what's undergoing the UCM. So when we write the sum of the forces, when we write the sum of the centripetal forces equals mv squared over r, m meaning the mass lies at ms, because the satellite is what's undergoing the UCM. The satellite is orbiting, is conducting a circular orbit around the Earth. The radius of that orbit is small r, and the satellite, its m, is ms, mass of the satellite. So the sum of the radial or centripetal forces is ms v squared over r. Well, what is that radial or centripetal force? Well, it's this guy right here, the green. It's given by Newton's universal law of gravitation. That is the centripetal force. So it's G me ms over r squared, because the two objects are the Earth and the satellite. So that's the left side. And it's equal to mass of the satellite times v squared over r. We're going to work this problem with numbers. Save that for another lecture. Then just what is a geosynchronous satellite? Why? Again, synchronous meaning its period, the period of one of its orbits, its period as it orbits the Earth is the same as the period of the Earth's rotation about its axis. Well, why is that the case? Well, the satellite remains in a fixed spot above the Earth. So you can, otherwise you wouldn't be able to send, for example, satellite TV. You wouldn't be able to watch satellite TV because the advantage of it being geosynchronous, it remains in a fixed spot above the Earth. So you can send and receive signals, because it's as if it's stationary, it remains in the same spot relative to any particular spot on the Earth. And we'll show that height, all geosynchronous satellites orbit the Earth at the same height, and that height is 3.58 times 10 to the 7th meters, a huge distance. But all right, but that's a geosynchronous satellite, and a future lecture will actually work the geosynchronous satellite problem. All right, let me go ahead and save this video and get it posted. But the important thing is that force between the satellite and the Earth, the force of the Earth pulling on the satellite, that radial force or centripetal force is given by G me ms over r squared, and it's equal to mass of the satellite v squared over r, because the satellite is the object that's undergoing the UCM. So on the right hand side, it's got to be mass satellite v squared over r. And there's the sketch, and it's clear from that figure that the radius of the satellite's orbit, r, the red r, must equal re plus h, where re is the radius of the Earth. Alrighty, let me go ahead and save this video.